Hi, my name is Oluwaseun Joseph Aribido. I'm a PhD student with the Center for Energy and Geoprocessing, led by Professor Ghassan Al-Rajib. The title of my presentation today is Weakly-Supervised Structural Interpretation Using Projection Matrices for Latent Space Factorization. You may often, during this talk, hear me refer to self-supervised because our method could also pass for self-supervision. And since self-supervision is a more difficult problem to solve than the weakly supervised, it is okay to hear me say self-supervised severally during this talk. There are several motivations for self-supervised learning in seismic interpretation. Deep learning is an imported method in seismic research for automated interpretation. There exists dataset disparity issue with publicly annotated datasets in Seismic. For instance, ImageNet here has about 1.4 million labeled publicly available images. MS Coco, KOR has about 1 million and several. However, F3 block, a popular seismic dataset, has only 1,500 labeled inline sections publicly available. The dearth of publicly available seismic annotated dataset is a huge motivation to study self-supervised methodologies in seismic interpretation. Another motivation is the disparity between natural images and seismic images. Natural images have very distinct boundary in their localization compared with seismic images. For instance, in this image, you have the annotation for a car. The edges of a car in this image are cleanly delineated from the edges of the background and other objects in this segmentation image. However, in seismic, you do not have that clean edge. In seismic, between seismic phases, expert or domain knowledge is necessary to be able to identify the various phases or the various structures in a seismic section. Because domain expert knowledge is needed for seismic interpretation, it is more difficult for the algorithm to be able to separate between various boundaries of structures or phases in seismic research. This is another motivation for why we study seismic interpretation using machine learning in a self-supervised setting. In a supervised learning framework, an interpreter labels part or all of the parts of the seismic sections of a seismic volume and partitions them into training and test set. We have an example of an annotated, partially annotated section here by a seismic interpreter who labeled various phases of this seismic section. If the interpreter has to label several of these for the machine learning algorithm, this is expensive because first, it is laborious to label several sections accurately by the interpreter before feeding that into a machine learning algorithm. Secondly, it takes an interpreter several number of years to be able to determine how to annotate this correctly or how to interpret this seismic section. After which, that will be passed into the annotated sections. The training set will be passed into a machine learning model. This could be an encoder-decoder architecture. This could be a segmentation framework. This could be a classification framework. And then we get some form of prediction. Now, we do that severally and apply that. We apply the land model on this prediction or test set, and then we're able to combine that into a labeled seismic block, whether within the same data domain or in a different data domain. This is the general workflow for automated seismic interpretation using machine learning in a supervised sense or semi-supervised sense. However, in our framework, we want to feed a raw seismic volume into our algorithm and have it label interesting structures by detecting important structures and separating them from non-important ones, which we categorize as background. Essentially, we want our self-supervised algorithm to focus on the important physics of the seismic amplitudes in this raw post-migrated seismic volume, and be able to identify interesting structures like we have on the right. To do this, we divide our seismic section into various categories. Each category has 3 consecutive sections taken at intervals of 10 apart. For instance, in the inline direction, we take the first 3 sections at interval 10 apart as category 1. We take the next 3 at 10 apart as category 2. Then we continue in that order until we exhaust all the seismic section in the volume. Now, for each categories, we break this seismic section images into 100 by 20 by 100 by 20 patches, and then we pass that into DBSCAN. DBSCAN is a density-based spatial clustering algorithm with noise. It was proposed in 1999 by Esther, and it clusters closely dense points together and labels outliers as noise. Eventually, for each category, we have about 30 clusters, depending on the hyperparameters selected for DBSCAN. Now, these 30 clusters would be merged together into fewer clusters using 2 algorithms we propose. Here we show how the merging is done. There are 2 algorithms proposed to merge the clusters together. The first algorithm merges clusters inside each category. The second algorithm, after merging these clusters within the category, then merges clusters between categories. And then we do that iteratively until we have about 4 categories left. And then we select the various clusters and we visualize them. Here we show a snapshot of the clustering result of DBSCAN and the hierarchical algorithm we built on top of DBSCAN. It was able to identify 14 clusters. However, we show about 8 of them here. Some of them are repeated. For instance, in the Horizon class, we had repetition. So we just merge those repeated classes together because the algorithm already clustered them together. Now, here, these are the various examples of 100 by 20 patches clustered by our algorithm. We had a chaotic, we had images from the salt dome cluster together. We had images from the horizon cluster together, which we label as horizon. And then the fault regions also had images clustered together into that class. We had some dipping chaotic regions or horizon lines also categorized in another cluster. And the bright spot region in the F3 block we also identified and clustered into another class. And then the top part of the salt dome, which has some of the chaotic sedimental regions as well clustered together. And then we had some other class, the classes that we could not place a category upon, we just label as unknown. Now, out of those classes, we select 4 categories. We select the horizon, the chaotic, the salt dome, and the fault for our experiment. Because the result of the clustering algorithm already gives us image level labels for each of the 100 by 20 and 100 by 20 images, we desire the self-supervision algorithm to be able to further label the pixels. Already we have the image level labels, but now we desire pixel level labeling. The kind of labeling we want is simple. We want to, for each 100 by 20 patch, we want to identify the most interesting geological regions. For instance, in this salt dome, from images taken from the salt dome, we want to be able to identify the most interesting geological meaningful part and then label every other part as background. Same thing as the images we get in the fault region. This is a kind of pixel level labeling with this self-supervised algorithm to give us. To do this, we pass this 100 by 20 and 100 by 20 images into an encoder-decoder architecture. The encoder reduces each of these images into a latent space, and then we pass that latent space into a decoder to reconstruct the image, the input image again. However, the latent space holds very interesting information about the image, but efficient understanding of the latent space is still hidden to researchers. In this work, we attempt an efficient separation of the latent space to identify features that belong to the to geologically interesting regions and features that belong to the background. And we're able to use a means, which we'll discuss shortly, to show how the partition of the latent space is done. So in our model, we feed each of those images, each of those 100 by 20 and 100 by 20 images from 4 clusters from the clustering algorithm into an encoder, E. The encoder gives us a latent space Z, and then we construct 2 projection matrices. Each projection matrix is a fully connected layer, and we project the latent space to 2 subspaces. The first projection matrix projects this latent space to Z1, and the second projection matrix projects the same latent space to Z2. We impose orthogonality between the space Z1 and Z2, so that Z1 and Z2 lie in orthogonal spaces to each other. Then we pass in Z1 into the decoder first, and then we pass in Z2 afterwards. And then we obtain 2 images corresponding to latent space Z1 and Z2. X1 hat corresponds to latent space Z1, and X2 hat corresponds to latent space Z2. We want X1 hat and X2 hat to be as different as possible, so we impose an L1 norm on the difference between X1 hat and X2 hat. And we get a specified result that gives us an annotation of the most important geological regions in the input image. We also ensure that the combination of X1 hat and X2 hat is able to reconstruct the input image such that X1 hat and X2 hat do not converge to weird representations. Now we take this output and apply that to label the pixels in our input images. But before that, we discussed briefly on the projection matrices. At initialization, we initialize P1 and P2 to be fully connected images, neurons, and we use a uniform initialization, and then during training, P1 and P2 converge to specified row space representation of the matrices that were initially passed in. These are the loss function that are added to the reconstruction loss of our encoder-decoder architecture. The first one ensures that P1 and P2 both converge to projection matrices, in the sense that the projection of P1 onto P1 should give P1. Same way, the projection of matrix P2 onto itself should give itself. That is what the first part of the loss function does. The second part ensures that P1 and P2 are orthogonal to each other. So this loss is added to the reconstruction loss. The reconstruction loss will act as a regularizer, and then we use gradient descent during training to solve this objective. These are the annotated representation. Here we just choose an example from the sort class. We pass in X, and then we get X1 hat and X2 hat as these 2 representation after training. X2 hat does not look like any image in our passed in dataset. Then we ensure that the combination of X1 and X2 leads to a reconstruction of X. As seen from the mean squared error here, the reconstruction is less than x1 hat and x2 hat. It means that x1 hat and x2 hat are factorizations of the initial input image. When we impose a difference, a sparsity difference between x1 hat and x2 hat, we get a specified representation as we can see here. Then we further threshold the pixels to remove the noisy regions so we can get a nice representation of the most important or the most conspicuous regions, geological regions in the input image, as you can find here. Our result, the proposed output is noisy, of course, but we will show that this is good enough for what we want to do, the regions we want to identify. Eventually, if we impose our output on each class of images, we get representations that are like this. Some regions are noisy and show very elaborate labeling, as we can see here, while some regions could be conservative and just label important edge regions. For instance, as you can see in the fourth class. In the chaotic class, in general, we also have noisy labeling of the pixels, but the regions that are identified lie in the most important region, which is the chaotic region, and all the other regions sometimes are left out, as we can see here. The salt region does the same thing, identifies the most important regions and leaves other regions unlabeled. Eventually, we compare our self-supervised technique with another weakly-supervised technique by Lauder. The performance of the algorithms are similar. In some cases, the labeling of the weakly-supervised framework by Lauder outperforms ours by making more elaborate labeling of the important structures. However, in some cases, the labeling are similar, as you can see in the fourth class, in which both algorithms mostly label the edges. We apply this to factorized sections, and we can see here that most regions of our framework are factorized. For instance, we use the image level labels and the pixel representation to train on the segmentation framework and apply that on a full section. For each, for instance, in inline 350, we are able to see that the algorithm separates out the horizon class and then leaves out the salt dome and leaves out the chaotic region. In the chaotic prediction, it's able to identify the chaotic region and takes out the fourth class and this salt dome and the horizon. The same here. This region is kind of a false positive, but this is where the faulted region was found. And in this case, our algorithm also detects the salt dome and leaves out every other structure, showing that it's able to factorize sections. When we extend this to 3D, we're able to see clearly the same delineation of various structures in the 3D region as well. We can also apply our algorithm to in the computation of attributes. We further compared against 6 attributes in literature: gradient of texture, saliency, GLCM, phase congruency, instantaneous amplitude, 2D gradient of texture. And ours is the proposed tool below. This proposes the foreground, this proposes the background. In the foreground, we're able to see that our algorithm can be used to identify important attributes in a seismic volume. It's able to identify the edges of the salt. It's able to identify some regions where the fault occurs. It's able to pick some part of the chaotic lines. The phase congruency and the 3D gradient of texture is a good computation, but our algorithm performs a clean separation of the important structures. In summary, we're able to cluster the seismic volume into image patches, factorize the latent space into orthogonal subspaces, learn the important geological features in seismic images, and use this to factorize seismic volume into various parts. Thank you very much. Our website is shown here, and you can see from our website several related papers that have been published as well. Thank you.